right? You remember I've got my CI is going to be equal to my mean value plus or minus T critical times my standard error, right? And so if I'm calculating confidence bounds around my means, I drop this critical T in there that I pull from my T table, right? And this is my central T distribution. My central T distribution is centered around 0. It's defined by a single parameter. That t-test is determined by degrees of freedom. Whatever that degrees of freedom is determines the t-family that I'm using. And my null hypothesis tests also use this central t-distribution, assuming a population mean of 0, right? Because again, the question is, assuming that the null hypothesis is true, how likely would it be to find these data, right? If the data I have is so very unlikely, I sort of claim evidence against the null hypothesis and claim that they're likely to have an effect. The problem is that confidence intervals for my effect size don't assume a mean of 0, and so then we have to go back to that non-central t-distribution, right? Again, because I'm not calculating effect size around effects of 0, because the very fact that I'm calculating effect size, I assume that there's effect to be had. And if that's the case, I'm saying that here's my central T, here's my non-central T of what's actually happening, right? So again, I can't use this to calculate confidence intervals around effect size, because my effect size is assuming a different distribution. It's assuming this distribution where this is my sigma for this, right? So I've got this distribution that's centered around whatever that sigma value is, okay? Now the problem is that we talked about the non-central T when we talked about some of the power calculations before. But what happens is this non-central T distribution, before we kind of drew it as a nice normal curve like the other one just for illustrative purposes, but my non-central T distribution isn't nice and normal, okay? It's non-symmetrical and it's not centered around 0, it's centered around some other value, right? And my non-central T is determined by two different factors. It's determined by my degrees of freedom and my non-centrality parameter. Both of these things are going to go through and change the shape of this non-central T distribution. My non-centrality parameter, or sigma, is going to be the point at which this non-central T is centered, and my non-centrality parameter is again going to provide me a difference between the true mean and the population mean under the null. So your non-centrality parameter, sigma slash NCP, again, it's just a metric of effect size. As your non-centrality parameter gets bigger, it's implying a bigger effect size. If it gets smaller, it's a smaller effect size. Questions? So basically what we're talking about is what we need to do is use a distribution, a sampling distribution that's not the same one that we use for all our test statistics. It's a different distribution, and one that's more complex, that's determined by a couple of things. It's determined by the size of the effect and also by the degrees of freedom. So we've got more uncertainty, there are more things to take into consideration, okay? And because my effect size is going to be a linear function of my non-centrality parameter, calculating confidence bounds around my non-centrality parameter will also give me a confidence bound around my effect size, okay? So if I think about, and so what we need to do, if we need to do this, calculate confidence bounds around my effect size, we can't do this directly. We have to do a little sort of like backwards work here. I'm interested in my effect, calculating the confidence bound around my effect size, but I can't do that straight away. What I can do is I can take that effect size and represent that as my non-centrality parameter, which gives me the difference between a null effect and sort of the actual stuff that I'm estimating. I can calculate a confidence bound around that non-centrality parameter, and then I can back translate the upper and lower limits of that the confidence bounds around the non-centrality parameter to get it back into the D metric. Okay. That makes some sense to people, and we'll walk through what this looks like. Okay. And then this is just Wilkinson saying that we should be giving confidence bounds on effect sizes for our principal outcomes, right? Because again, remember that a confidence interval is just a point estimate, or excuse me, an effect size is just a point estimate just like any other point estimate we've got. It's measured with error, right? And so our data will support a range of effect sizes in the population. My point estimate that I've got is my best guess, but my data would support effect sizes ranging from sort of here to here. So the thing about the non-central t distribution, my non-central t is going to be centered at my non-centrality parameter, which can take any positive or negative value. If my non-centrality parameter is 0, then I've just got a central t distribution, right? Think about this, the way I like to think about this a little bit is, let's say I have a t distribution, a nice normal t distribution, and I grab that at the middle and I start pulling it, right? As I start to pull it, it's going to distort it and change it, and the more I pull it, the more it's going to distort that shape. This is essentially what's going on with my non-central t. My non-central t distribution is skewed very strongly at low degrees of freedom, and less so as degrees of freedom increases, right? So as the number of people I have in my sample increases, my non-central t gets a little bit more normal, but still some marked skew as my effect size increases. As you can see here, as I start to go through and pull this out, as my non-centrality parameter gets larger and larger and larger, it starts to stretch that distribution out and make it look really weird. For any given non-centrality parameter, my non-central t approaches my central t as my degrees of freedom increase, but this is very, very gradual. And even with a small absolute value of my non-centrality parameter, still we're maintaining a skew with relatively large degrees of freedom, okay? So again, think about that t distribution, and as I start to drag that out, as my effect size increases, it's going to distort the shape of that, and the shape is going to be determined by how far I pull it out and how many people I have. Now, if I've got really, really massive samples and sort of maybe non-centrality parameter that's not that big, my non-central t might look pretty normal, but that's going to take a while, okay? So people see kind of the features of what's going on with this. We're using a different distribution that's not centered around 0, because we're not assuming the null is true. We're assuming I have an effect to be had, and I'm dragging that t distribution out to correspond to that. Okay. So what I need to get calculated confidence bound around effect size, I need to get a non-centrality parameter. But getting a non-centrality parameter is kind of complicated. Like before, when I first started teaching this class, it was like me sort of iteratively entering values in R to try and like sort of find like a value that would come up, and so it was a real pain. But over the years, sort of people have started to recognize this more and more. I'm assuming they're all YouTube subscribers and have like watched all my lectures, and really, so it was me that really pushed SPSS to start doing this and incorporating this in their stuff. But there are other ways to go through and do this. SPSS does this for you now, so long as you're careful and you know what to report and look for. But we can still go through and do this on your own by hand. Lucas, to speak to your question, what I might do is, if I had an effect size based on a study, but I'm worried that that effect size might be a little bit big, what I could do is take that effect size, and if there's enough information in that article, what I might do is go through a calculated confidence bound around that point estimate of that effect size, and I might, if I wanted to be conservative, say, I'm going to just be conservative. This data, this study would support a low bound effect size of this, and this is what I'm going to power my study to as a conservative approach, okay? And that would be real boss, and it would be sort of a high level thing to go through and do, right? There's some problems with it in practice, because what we'll see is our confidence bounds for effect sizes get really, really big. Our estimation of effect sizes are really, really imprecise. Our means can get pretty big, pretty good, but we have to have really, really large samples to get a precise estimate around those estimates of effect size. But if I wanted to go through and do this, what I could in this, so here's a link to a little calculator that's put out that makes it really easy to go through and get your non-centrality parameter. Here I've got a t statistic, f statistic, chi-square distribution. I just go through and determine what distribution I want. Here I put in a t distribution. Here I put the value of my tested statistic, not my critical value, my actual t statistic. I've got my degrees of freedom. I say I want a 95% confidence bound around that. and then I hit compute, and it's going to give me a confidence bound for the lower, upper, around delta. Delta is just my non-centrality parameter, or sigma. Like the notation on this is not ever the same, but this is what's giving me a lower and upper bound for my non-centrality parameter. So calculating, so once I've got my calculation for my effect size, or once I got a calculation, upper and lower limit for my non-centrality parameter, calculating an upper and lower limit for my effect size gets really easy, okay? For my single sample test, I just take the lower bound of my non-centrality parameter divided by the square root of n, upper bound divided by the square root of n. That's going to give me upper and lower bound for my for my effect size d. Okay. For an independent sample test, I take my lower estimate for my non-centrality parameter, multiply it by 1 over my first sample plus 1 over my second sample, take the square root of that. Got the low end. Here's the high end. My repeated measures, again, this is identical to my single mean test because a paired sample test is just a single sample test on a column of change scores. The thing that starts to get tricky with this, if you're doing this by hand, is the estimate, sort of the point estimate that you're calculating around is limited to that d-diff metric that we talked about, where we're taking the mean of the different scores over the standard deviation of the different scores. Now, we talked about using the standard deviation of the different scores as not great because I don't know how to interpret this. This is the mean, this is the standard deviation difference over the standard deviation of the difference. It starts to get weird and circular. But the problem is for calculating confidence bounds around an effect size for your repeated measure. If I were to try and do this around like glasses, use glasses delta as my point estimate, what I'll get is confidence bounds that don't actually contain my point estimate, right? As you work through all of this, if you're doing this by hand, what you should be doing is whatever estimate that you're using for your standardizer should be the same estimate that's going into the calculation of your test statistic. So for a single sample test, it's easy because you just have one, it's just the standard deviation of your one sample, right? For your independent sample test, you should be using glasses delta. Your point estimate should be the estimate using the pooled standard deviation. The pooled standard deviation of what goes into the calculation of your test statistic, and that'll make sure that your confidence bounds are sort of centered around the right point estimate. Here for your for your repeated measures test, we can go through. There's a lot of different metrics that we can use to standardize. The problem is if I standardize using baseline standard deviation, and I need to go through this process, the variance measure that's going into the calculation of my test statistic is the standard deviation of different scores. And so what I'll do if I use the wrong metric, I'll get a confidence bound that doesn't contain this, and then you can't report that, so it doesn't make any sense, right? So you just need to be cautious and careful when you're doing this, okay? Here is a link to YouTube, so it's just me walking through doing this process. If you want to see me actually walking through it, it's not terribly complicated, but if you just want to walk through, you'll go through and find it there. And here what we're talking about, Lucas, we say, again, looking at using these confidence bounds to estimate a range of power values, right? So like I could go through and say, based on this, I would say that any sample of anywhere from this to this would accommodate the range of effect sizes that would be supported by this study. Again, that would be pretty high level stuff. You don't see it most of the time because it's uncomfortable, because the low end is probably a really, really, really massive sample, and so people will say, well, it's not really worth going through and doing it. But if you just wanted to do it for your own knowledge to understand what you're probably facing, it wouldn't be a bad idea. Okay. Questions about this process? All right. So, and I will say, again, we go back to talking about sort of the precision on confidence interval estimates around my effect size. These tend to be really, really big, really, really wide intervals. They're also not balanced intervals. For my for means, right? We calculate confidence intervals for our means as sort of my point estimate plus or minus my standard error, and so it's balanced. It's right in the middle of this, right? Here, because we're not using non-central t's, my point estimate on my effect size won't be dead center in the middle of my interval. It'll be closer to one side than the other because my distribution is skewed off, right? So they're not going to be centered there. And again, with this non-central t, they just end up being really wide. And people will make an argument that say like, well, calculating confidence bounds around your effect sizes isn't useful because the things are so large that, you know, what you'll find sometimes, you'll find evidence for an effect. So based on my hypothesis test, I find evidence for an effect, right? And I got evidence for an effect size that's say like 0.5, right? But then if I go through and I calculate a confidence bound around my effect size, I'll get a negative value on the low end and a really high value on the top end, right? Remember that your effect sizes are a different thing than your null hypothesis testing. They're separate things, okay? So your null hypothesis is telling you have evidence for a non-zero difference across your groups or whatever, but all that's telling you in terms of your estimate of your confidence or your estimate of your effect size is really wide, right? This could mean anything from sort of 0 to something really big, and people will say, well, this is a reason why this isn't a useful process, and so like we shouldn't be sort of trying to incorporate confidence bounds around my effect size. I would counter with that's a practical implication of being that's a sort of response to being uncomfortable with being aware of how uncertain our estimates of effect size are. Unless we have very, very large samples, we can get an effect size estimate and be very confident and happy about that. But if we were to go through and calculate our confidence bounds around that, it could be anything from really trivially to small to really, really massive, right? We should know that as we're making interpretations to say, hey, in the real world, my data would support anything from anything that's sort of inconsequential to really massive. What we need to do is think more carefully about going through and sort of being careful about the conclusions that we draw from our data and sort of planting a flag as like, oh, this is a large effect, when in fact, it might be something really small. My data is still saying that, yeah, there is an effect there. It's just a lot of uncertainty in sort of what that's actually looking like. Okay. So these last couple of slides, we don't need to go through and work on this. This is just a couple of examples of work, actually things that I've published, where going through and taking a look at sort of effect sizes and then confidence bounds around that. And so ways I've tried to go through and incorporate this to really hit home with so what's going on here. We're looking at change in bipolar disorder. We say absolute change in patients with bipolar disorder was even more pronounced. Point estimates of effect and lower limits corresponding confidence intervals indicated at max a full standard deviation of improvement across groups, right? So again, here I'm saying, like, even if we go through and look at the low end of the effect size estimate, we're still a full standard deviation difference pre and post treatment. So just, again, trying to bring things in to make a strong argument, make, hey, this is what we can say about stuff. Same thing here. We're going through calculating effect sizes here and then providing confidence bounds around that to just kind of, you know, trying to give people an idea. Hey, if anybody were to use this and go through and say, okay, well, here's our point estimate, but here's kind of the range of values that's going on with this. And so, again, both of these samples, or both of these studies had pretty large samples. This one had about 200 folks, and the other one had more than that. So the confidence bounds around my effect sizes are reasonable. But if you start to get smaller samples, they start to get really, really big, as you'll see in examples that we'll go through and do. So just, again, not filtering out the stuff that's inconvenient to think about, but using that to sort of develop stronger, better interpretations. Okay. All right. Take-home points, references for effect size, and that's where we're at with stuff. Okay. One thing that just sort of hit me on this, sort of in terms of your interpretations, really like sort of what people are going through and incorporating sort of practical interpretations and things like that. One thing you don't need, like, sometimes sort of like if you feel the knee-jerk urge to say, oh, so we need more research on this to really determine what's going on. That's fine, but that's always going to be true. So if it's always going to be true, you don't necessarily have to write it. What would be a stronger way to go through and do that? Like, hey, this sample was just looking at university students and what they're actually looking at might differ, so it might be important to look at other groups or communities, or the sample was really small, and so like a lot of imprecision with this stuff. So just thinking about like not just defaulting to more